Finite state machines. Now we are familiar with the basics of combinational and sequential logic design, and it's time for us to understand this finite state machine and work at the RTL level. I don't think that I really need to explain what is RTL because we have been discussing about it on and off throughout this training course. So let's move on and see how we can use this FSM to design any kind of complex logic circuit. Okay, this is our proprietary material. Please read this note. Why FSM? Before jumping into FSM design, we need to know why we go for finite state machine. Let's say we want to design a chip for automated teller machine. You must be familiar with the ATM. You insert your credit card or debit card, you get the cash. But actually, it's not going to be very simple and straightforward like this. There could be many possible scenarios. For example, you inserted your card but pressed wrong PIN number. Then what would happen? Or if someone is trying to misuse your credit card, then how it has to protect your information, user identity. Or the machine is running out of cash. Then what would happen? So like this, you have to think through various possible scenarios. Now, when it comes to finite state machine, what actually we do is we define each scenario as particular state. So this FSM will go through many states. So to design finite state machine, you have to identify the possible scenarios and you need to define each scenario as state. Then how the transition is going to happen? You give some set of inputs and based on the inputs, the machine will get into a particular state. And for each state, we are going to define particular output. That's how fundamentally this FSM works. So what we do is we understand the functionality and then based on the functionality, we define FSM with multiple states. Now let's look at this example, how this ATM chip works. When you put on power, this ATM will be initialized with ideal state. This is the initial state and everything is going to happen from this ideal state. Now this machine is out of service, so automatically it gets into out of service state and then automatically it comes back to ideal state. You inserted your card, the machine is working fine. It gets into pin entry state. You pressed wrong pin, so automatically it goes back to ideal state. If you press valid pin, it gets into next state. Then based on the type of transaction, it will get into different state. You want to check the balance. You don't want to withdraw money. So it gets into a state called display balance. After displaying the balance, automatically it goes back to ideal state. Now you want to withdraw your money. You enter the amount, but you made a mistake. Invalid amount, so it displays invalid amount and automatically it goes back to ideal state. In case you entered valid amount, then it gives you the cash and then automatically it goes back to ideal state. This is how you can approach this design. But again, this chip is not going to be very simple like this. I'm showing only few states. But to design this chip, you have to think through all possible scenarios. There could be many scenarios. Okay, that's fine. After designing this FSM, what actually we do? We actually extract the logic circuit from this FSM. So what we do is we identify the flip-flop, what kind of flip-flop we want to use, T or D or JK flip-flop. Then based on the excitation table of that particular flip-flop, we define logic function and then we try to minimize the terms. And based on the minimization, we create optimized logic circuit. This is what actually you are going to explore during advanced digital course. But in reality, we don't do all these things manually. That's what you need to understand. In industry, what actually we do is we define this FSM and straight away we write source code based on this FSM using Verilog or VHDL. This is what I'm going to teach during Verilog programming class. How to define finite state machine in HDL. Once you understand this coding style, then you would be able to define FSM, any kind of FSM easily in Verilog. Now what happens is, we write the source code and then we use synthesizer to generate the logic circuit. So producing logic circuit is completely automated with the help of synthesizer. The synthesizer is going to compile your source code, and then based on the definition, based on the number of states you define, automatically it is going to produce the logic circuit. So finally you will come to know how many gates you really need to implement this particular chip. So the whole process is automated. The minimum thing that you need to understand is how to design this kind of FSM. Okay, when we go for finite state machine, if the functionality of any sequential logic circuit is very complex, then we go for finite state machine. Let's say the logic circuit moves through various possible states. There are different kinds of control inputs. For a particular set of inputs, it gets into a particular state, and based on the state, it produces particular output. Again, there are different kinds of inputs, and based on the inputs, it gets into new state, and based on this state, it produces different kind of output. Like this, the circuit is moving through various possible states. Now, if you consider the number of states, it's huge. So in this case, what we do is we use finite state machine to define this kind of complex functionality in terms of states. It's very straightforward. So it's a systematic way of specifying sequential logic. Basically, we can classify them into Mealy model and Murray model. Now let's look at the difference. Before analyzing the difference between Mealy and Murray, I want you to understand the concept of finite state machine. You take any FSM, there will be three major blocks. The first one is combinational logic. It's called next state decoder logic. It produces next state. Whatever the state it produces, it will be stored in sequential logic. This is the second major block. And based on the state, the output block is going to produce the output. Again, this is combinational. So there are three blocks. Now, look at this combinational logic, next state decoder logic. It produces next state based on the input and current state. Now, let's look at the difference between Mealy and Murray. In case of Murray, the output depends on only the current state. Look at this combinational logic. It always samples the current state, and based on the state, it produces the output. But in case of Mealy, this is the major difference. The output depends on both input and current state. Thanks for watching this video. Thank you.